Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to start a new unit, and this is Pure Maths 1 Functions, Part 1 Composite Functions. But before we get into the composite functions, we'd like to do just a little bit of review. And in our review, we want to look at three things relatively quickly because in the functions unit, most of the things that you learned in IGCSE material is repeated but just advanced in the Pure Maths 1 and the A level. We'll expand on what you learned in the IGCSE, but we do need to do a little bit of review. We want to look again at definition as to what makes a function. The notation is very important. It tells you the instructions of what to do. And then a simple example of an evaluation. All these three you should already be familiar with. Just want to briefly cover those. And you'll see that some of the things that you learned in IGCSE, like evaluating even composite functions and inverse functions, are all things you should have already learned, and we're just going to maybe use a little bit more complicated equations. We're going to expand on that to further your understanding of how functions work. And let's talk about the focus here really quick before that we do our review and get into composite functions. The focus for Pure 1 mathematics with functions is mainly twofold. Most of the question types with functions will either be algebraic or trigonometric. We're going to focus on the algebraic. The algebraic is going to have a heavy overlap with what you just saw in the quadratics unit. In fact, oftentimes these question types are blended together. Okay, you're going to take what you learned in quadratics, what you learned in functions, and you're going to blend. You're going to see that the question types are often connected and correlated. So you're going to see things like completing the square again. You're going to end up with quadratics that you're going to have to factor. You're going to take the things that you learn in functions and apply it to quadratics. So there'll be a lot of overlap, which is really good because it helps you review quadratics and it helps you also understand the nature of functions. So that is going to be our main focus as we go through the functions unit. Part by part, topic by topic, our focus is going to be algebraic, and you're going to see the heavy emphasis on quadratics. There is also, in the functions question type, there is another emphasis on trigonometry, but we're going to wait on that. If you see functions with trigonometry in worksheets or past papers or something like that, just wait for a while until we get to the trigonometric unit. Once you understand trigonometry, there will be in part 7 of the trigonometry unit, there'll be a special video just for trigonometry and functions, whether you want to call them functions with trig or trigonometry, with functions, same thing. But you'll see the correlation in that video of what you learn in functions, what you learn in trigonometry, and those blended together. But it's important that you further your trigonometric understanding first. So we're going to just wait on those until part 7 of trigonometry. We're going to focus on the algebraic part. And if you pay attention to how functions work, then it shouldn't be too difficult for you then to apply that to trigonometry later when we get there, okay? So let's go back to review. First of all, what makes a function a function? What is its definition? Well, the easiest way and the fastest way to determine whether An equation is a function is simply by looking at its graph. Does it pass the vertical line test? So just really quickly, if you take a line and you pass a vertical line across your graph slowly from left to right. And so if you look at any imaginary cross section as you're moving your vertical line across your graph, as long as it's only touching your graph at one point from left to right, then that can be classified as a function. So if you get to, so lines, all lines are functions except, of course, the vertical line itself. So most lines classify as functions. Only the vertical line, which would be like an x equals a number, that would not classify as a function. Parabolas. Most, or we'll say half of your parabolas classify as a function. As you move your vertical line from left to right, here's your vertical line, again you see it's only touching at one point. The sides are not going straight up. The sides are still going over and over. It's just that the rise over run is becoming more steep, but it is still moving left as it goes up. So it never gets to a place where it's going straight up. So your parabola that either faces up or down will classify as a function. We're going to see that this is going to be a huge emphasis that we deal with in functions, is your parabolas that face up or down. There are left and right parabolas, but they do not classify as a function, and as such is probably why a lot of curriculum ignore the left and right facing parabolas. So instead of a y equals x squared, this would be a x equals y squared type equation. So as you can see, it fails the vertical line test because as you move your vertical line across your graph, it touches in more than one place. So this is not a function. So some curriculum will teach the left and right as equations and graph types, but they are not included in functions unless you break them in half, which is a different story. You'll see that later. We'll break these in half in order to create an inverse function. So I don't want to really talk about that now. And also circles also are not functions, which we'll get to circles in coordinate geometry unit. And so circles are not classified as functions. Again, it is possible to break them in half and treat the top half as a function and the bottom half as a function, but that's really a little bit more advanced than what we need to do. So the important thing is that you understand the definition of a function. Really, practically speaking, it means as your graph moves from left to right, it doesn't fold back on itself. Your graph will continue from left to right. Might go up, might go down, might go in a wave, but it will continue from left to right. It won't fold back on itself like a circle does. Circle comes back on itself. Your sideways facing parabolas, like the ones facing this way, it goes, but then it comes back on itself. So you're not going to have any of that. All of anything that's a function will progress from left to right on a graph. So that at least will give you an idea of what is a function conceptually. So again, the easiest way is with a vertical line test, and that way it doesn't get too complicated. Now, function notation. The notation and is what drives the math. It tells you what to do. It gives you the instructions. So it's very important that you learn the function notation so that you know what it is that you're supposed to be doing. So with function notation, Cambridge likes to use two different notations. And the first one is this f with a parenthesis and x. And we read it f of x. It means your function is written in terms of or with the variable x, okay? And when they have several equations that you're working with, they'll call the first one f, and then they might call a second one g, and if they use a third one, they would call it h. But most of what you're going to see is going to deal with f or g. If you see a g, it means that's the second equation. The first one would be f of x. This one is g of x. Okay, so this is the function that I'm going to use. So as I go through this unit, I will always use this notation here. Cambridge also will use this, but Cambridge also uses this form here, has f with like a colon, x, and then this symbol here. I don't like to use that simply because it's more complicated in writing. It's not really necessary, so I will use this notation in all of my videos. But you should be aware when you see this in the Cambridge, it means the same thing as this. It's just a different notation format, okay? What's important is that you realize, like up here, the left side of your equation is the function notation. It is notation, it is not math. In other words, you don't do any math on the left-hand side. All the math is done on the right-hand side. So this is simply telling you that there is a function, it's written in function notation, so it passes the vertical line test, and this function is written with the variable x. When you look over here, you see an x. So the 2x minus 3, this is where your math is taking place. This is only telling you what to do or what is, here at the moment, okay? So again, when you get into evaluation, then it tells you what to evaluate. So if you have, say, let's make us a function here. Let's say we have a function of x that is, say, a quadratic, x squared minus 3x plus 5. And you see f of 3, f of 3 again is telling you what to do. It's telling you that this classifies as a function, which we can see, it's a parabola, passes the vertical line test. You don't have to worry about it. If it's in function notation, it automatically satisfies the requirements of a function. They want you to evaluate it for 3. Well, that means you put in a 3 in every place you see an x. So your x is being replaced with a known value, the value 3. You plug it into your x's, wherever you see the x, and then you simplify it. So you get 9 minus 9 plus 5. Well, the 9's cancel out and you just get 5. So you can say f of 3 equals 5. You can also plug into it an algebraic expression. You don't have to plug into it a numerical value. You can plug into it an algebraic expression. So that would become something like x minus 2 squared minus 3 times x minus 2, and then your plus 5 there at the end. And you can simplify it out, and depends on what you want to do with it. Back in IGCSE, you had expressions that you had to come up with, and you might have had an occasional function equation, meaning they give you f of x equals, say, 13. Well, you got to take your function and set it equal to, and then solve it, okay? So we're going to see a lot of that in the work that we do. In fact, our composite functions usually aren't just a standalone concept. They're usually blended with some other aspect that you need to do. So I don't want to really demonstrate function equations at this point because we'll get into it as we go through. But I just wanted to quickly review these things. These are fundamental and basic. So before we expand on our function information, definition, vertical line test, notation, that's the primary notation. We will look at the appropriate notation as we move forward. So this is just the basic notation. Okay, so I don't need to get into the others right now. In our next videos, we'll introduce the notation as we get there. And then how to evaluate, you should already know how to do that. So this should be review. You should already know this, but it is fundamental just in case you're coming into this video and maybe you forgot some of those basics. Our focus, we're going to focus on the algebraic part. Again, we'll wait to the trigonometric functions until the unit on trigonometry. Okay, so let me just get rid of this really quick, and we're going to focus right here on composite functions, and we'll go through some examples. Now, in this one, I put the g of x. I did not put up the f of x function. There is an f of x function in this particular problem, but it is not involved in the composite function part. So until we get further along in the functions unit, I want to focus on one topic at a time. So this is a composite function notation. You see two letters next to each other. Sometimes you see f of g of x, sometimes you see g of f of x, and in this case you see g of x. So what's important with a composite function is a function within a function. It's like those, what are those Petrushka dolls, or I forget what it is, those like little dolls that you take apart and there's a smaller doll inside and you take it up and there's another. It's like that. It's one function inside of another function. So what you want to do is you want to work from the inside out. You're going to work from what it is that you're supposed to evaluate, and you're going to plug that into the function that's stated most close to it. Then that value you're going to take and plug it into the next function that's stated. In this case, we're putting the g function into itself. So all they asked in this particular question is to find an expression of g of x, okay? So to do that, first of all, we have an x, meaning we're not replacing, say, a number into it. We're just leaving x as x. So we don't have to change anything. If there was a 3, we would have to plug the 3 in first and simplify that. But it's just x, so x replaced as x doesn't change anything. So that gives us our g of x. Now our g of x is going to put back into the g function again. So our g of x is 2x minus 3. So now this x is replaced with a 2x minus 3. We're putting the function back into the function itself. So it would look like this, 2. Now I replace the x of this g with the g of x. Okay, so the x of this g, the outer one, is replaced with the inside box, which is g of x, 2x minus 3. We're working inside out. X is just x. G of x plugged into g of x again. Don't forget this minus 3 at the end. I notice some students start off with the 2 and they put in the 2x minus 3 and they forget to attach the rest of your original g function. So here you see the 2, here you see the x, which is now replaced with 2x minus 3, and here is your minus 3. So be careful to get that lined out. Then you just simplify it. This one is an easier question type here. So distribute, you get 4x minus 6 minus 3 So this equals 4x minus 9. And you have now the expression for g of x, which is a composite function and quite simple. So these are going to get a little bit more complicated. And like I said, they usually don't ask the composite question as a standalone. It's going to be incorporated usually with a function equation or a composite function equation that you have to solve. So let me set up an example and we'll go from there. Okay, here we have another example where we have an f of x function and a g of x function. They're a little bit more complicated. It wasn't as simple as like the linear one that we just saw in the previous example. And off to the side, Cambridge provides for you a domain statement. Now, back in IGCSE material, they didn't really require you to interact very much with the domain statement. In A-level math, you're going to get more involved in understanding domain and range, and you're going to have to get involved with even creating some of those statements yourself. For right now, it's provided for you. The x greater than 0 is both the domain for the f of x function. It is also the domain for the g of x function. Now, it's important. Even though it doesn't really affect the outworking of the problem, it's important that you start understanding the meaning of the domain statement. Because there's a fraction here, it means x cannot equal to 0. You cannot divide by 0. So 0 is one number on your number line that is excluded from the domain. The domain are the possible values that you can plug in for x. So 0 is not one of them. So to avoid that, they could have said just x cannot equal 0 if they wanted to. But they just chose to say x greater than 0, meaning they're only taking positive values for this particular example. So whenever you see a fraction like that, you can expect a domain statement either telling you what you cannot use or limiting the values that you can use so that it does not include a value that you can't use. Same thing over here, you've got a fraction. So in this case, if it had not already stated the x greater than 0, you could work this out and find out that x cannot be a negative 1/2. Negative 1/2 times 2 would give you a negative 1. Negative 1 plus 0, or a negative 1 plus 1 gives you 0. You can't divide by 0. So the domain statement is very important. So we might as well introduce it into your thinking now so that we can develop your understanding of the domain statement. But for a composite function, they provide for you the domain statement and just are asking you to follow the directions that are provided in the notation. So here we have find an expression for, we're not doing an equation yet, just find the expression for f of g of x. Notice we have two functions and we work from the inside out. It's a box within a box or a function within a function. So the g function is being put into the f function. Notice again, there's no value, there's no numeric value that we're substituting in. We're just leaving it as x. So we don't need to change anything initially. So our x is already the understood or the variable that's expressed in our g function. So there's nothing there. Then our g function, this function is now going to be placed into the f function. Work from the inside out. And so that means we have to replace our x in the f function with the g function. So that's going to look like this. We're going to get f g of x. That's the notation telling us what to do. There's no math on the left. On the right, we get 3 divided by 2 times. And now we replace our x from the f function with the g of x. So this becomes 1 over x plus 2, and then we finish with plus 1. So here we have 3 over 2x, our x. The g of x is being put into the x of the f of x. So the g of x function replaces the x. Okay, the g goes into the f, the inside into the outside, and you finish off with plus 1. Now, we need to take this and then rearrange it into this form over here. In other words, there's not this complex fraction. Notice we have a complex fraction here. We have 2 division bars. We need to simplify that. So distribute the bottom, get 3 over this, distribute this, so we get a 2 over x plus 4 plus 1. So we distribute our 2 out in front. This then obviously becomes 3 over 2 over x plus 5. So we need to get a common denominator here. So we need to multiply this top and bottom of, to make a whole number a fraction, just put it over 1. We need a common denominator of x. So we need to multiply top and bottom by x. So that gives us a 2 plus 5x all over x. When we multiply top and bottom by x, it now gives us a common denominator, so we only need to write it once. And in the numerator, we have 2 plus 5x. This is still a complex fraction. And it's really important in complex fractions, and I notice some students fail to recognize the difference in your division bar. This division bar up here is your major division bar. It is longer than this division bar here. That's significant. Your division bar tells you the difference between the numerator and the denominator. So the 3 is the numerator, and the 2 plus 5x over x, that's the denominator. So this is our major division bar. Now, when you divide by a fraction, you invert and multiply. Hopefully you remember that from earlier algebra that you've had. So this flips over and becomes x over 2 plus 5x. So your major division bar identifies your denominator. Your denominator is the one with the fraction in it, not the numerator. It's what gets flipped over. So the bottom goes on top, the top then goes on the bottom. We multiply this out. We now get 3x over, and they want it in this order, so we put the 5x first plus 2. So now we've matched the form that they want. And if you're identifying your parts, A equals 3, B equals 5, and C equals 2. So we got a little bit of algebraic practice here. Like I say, the focus is mainly with algebra, and it's a good review for us for algebraic skills, but you have to understand the notation because you need to know what is expected of you and how to set it up in the problem. Okay, so let me set up another one. We'll get into composite functions, equations that we are solving. Okay, here we have a more complicated question where we have a function within a function involving a quadratic that is already in kind of like the square form. And it's in an equation that we need to solve, and they want the form to be an a plus root b, meaning we're going to end up with radicals in our answer. They want like exact answer, not decimal answer. So we've got a lot of different things to consider. Our original function form, the composite function itself, the equation that we're trying to solve, and the final form of our answer. Also, if you notice, again, just to point out the domain statement, x greater than or equal to 2, Won't take time to explain it right now as far as in depth, but notice that they didn't say, normally a parabola, you can take everything, not like a fraction where you can't divide by 0, but a quadratic fits function notation. There's no problem with, because you don't have any fractions, so you don't have any value that technically you can't use. But the fact that they have x greater than or equal to 2, in this particular question, they identify this as a one-to-one function, meaning it has an inverse. We haven't got to inverse yet, so this domain statement has to do with that. You don't need to worry about it right now, but you should look at the domain and consider its importance with the function. It does have an importance, but we're not ready for it yet. So let's get back to our composite function part here. And we want to put our function within a function. You're going to have to make a choice. Sometimes it's a little difficult to know which choice to make, especially when you have this complete the square form. But we need to understand they put it in this complete the square form on purpose, okay? One thing I notice students do is when they see something like that, they automatically want to expand it into the polynomial form, you know, the ax squared plus bx plus c form. Sometimes you might need to do that, but you should ask yourself, why do they put it in the complete the square form? We don't really see why at the moment, but let's just trust that it's that way on purpose, okay? So don't be too quick to expand everything that you see as a square. X minus 2 squared, yes, it equals x squared minus 4x plus 4 plus 2, and you can simplify it. But don't do it unless you have a reason to, okay? So let's assume that that is on purpose in this form. So when we go to set up this function, we have this, and we're replacing the x. Notice our x is already x, no problem. We're not putting in a number. Then our f of x has to be put into f of x again. All of this has to go into this x. So this is this big outer parenthesis. Now x is all of this, x minus 2 squared plus 2. This is the x. Minus 2 squared plus 2. So it looks a little intimidating, but it goes back to what I said. They've set this up for a reason. And if you notice that when we plug our f of x into f of x, and then it's an equation on top of that, so we put the equal 51 at the end, that this plus 2 and minus 2 actually cancel out, okay? So this cancels out, and it leaves us with an x minus 2 squared plus 2 equals 51. Well, when you have an exponent raised to an exponent, you just multiply. So this is really an x minus 2 to the 4th power, okay? Plus 2 equals 51. So now we've simplified that. It doesn't look very simple, but we've at least followed the math. Now we have to get and solve for our x. So let's get rid of this this plus 2 up here. Let's minus 2 to both sides. And I'm going to write it up here. We might need some more space. That's why I erased this over here. So we're going to have x minus 2 to the 4th equals 49, okay? Now we need to take the 4th, to undo a 4th power is just like undoing a square, you square root. Undoing a 4th power is undoing a 4th root. So we need to 4th root, so don't forget to put your index number, both sides. Fourth root both sides, that cancels that. That leaves us with x minus 2 equaling plus or minus the fourth root of 49. Okay, now we add our 2 to both sides. These are unlike terms, so x equals 2 plus or minus the fourth root of 49. But notice this shows a square root, not a fourth root. So we have the a part, but our root b part needs simplified a little bit. So I'm going to write that over here. We can write 49 as a number squared. We can write this as x equals 2 plus or minus the fourth root of 7 squared. Okay. Now remember, radicals can be written as fractional exponents. So if we write this 7 as a fractional exponent, it's power over index number. Here's the exponent or the power. Here is the index number. This is the exponent. This is the radical. Power over index number gives us a 2 force. And a 2 force reduces to 1/2. Okay? So this can be rewritten as x equals 2 plus or minus the square root of 7. So the fourth root of 49 is the same thing as the square root of 7. So write it into the form of this, and notice x has to be greater than 2. Again, we come back to our domain to make sure that our solution set fits with our domain statement. Now, this is a composite function. Later, we'll talk about domain statements with composite functions. But in order to plug this value in to either f function, it has to satisfy this domain statement. It has to be greater than 2. So notice this says a plus root b. We don't need the minus because it will take us into the area of the domain that we don't need to go into. So we just want the plus. Obviously, if you subtract from 2, you get less than 2, not greater than 2. 2 plus root 7 will be greater than 2. So let's see if this makes sense. We have a fourth power equation, means we should have 4 answers. Why do we have 2 answers? Well, most likely this would have been if you had moved the 51 the other way, just so that you can pay attention to little clues that can help you know if you're doing it right. Fourth power equation means you should have 4 answers. So if you subtract this the other way, you would get a minus 49 equals 0. Means you have a difference of squares. If you have a difference of squares, then that means that it could factor, it'd be like another way of doing this instead of doing it the way I did it. You could have an x minus 2 squared plus 7 and an x minus 2 squared minus 7. Now, the reason why I didn't do it this way is because I think factoring a difference of squares off of a fourth power might be a little bit much for you to process, maybe not, but you could have factored it as a difference of squares. So here's your a plus b, your a minus b. Notice you have a square here, meaning you would have gotten 2 answers from that. Here's a square here, you would have gotten 2 answers from that. You do have 4 answers. So I'm guessing that you're going to get duplicates. In other words, you're going to have 2 answers identical and another 2 answers identical. There probably could even be another way of doing this, but or here we see that actually there's going to be two answers that are imaginary. That's where this comes from. You're going to have two imaginary answers here because you're going to have a square that equals a -7, and when you try to square root a -7, so this part right here actually are two imaginary answers. So what we ended up with are the two real answers. That's why we only got 2 instead of 4. And then the one that we want in particularly is this form right here. So there are things that you can kind of do to double check. You don't always have time to do that, but you do need to get used to the idea of looking for how your answer set fits domain and things like exponent. So just something to keep in your thinking. If you didn't understand that now, it's okay, don't worry about it. It's not important to this particular question, but it is something that you should develop, and I'll mention it from time to time down the road. So let me set up for one more. Okay, here's our last example for composite functions, and you'll see that we have two separate functions. F of x equals 2 over 3 minus 2x, so we have a fraction. So our domain statement, x cannot equal 3/2, is because we don't want to divide by 0. Again, it's provided by Cambridge, but you should always just look at that. It means any other value is okay. So you can either say what x can be, or you say what x cannot be in your domain statement. So here's f of x, then g of x is this 4x plus a, and this means that x can be an element from the real set. So basically any number, except for obviously imaginary numbers, complex numbers. So all real numbers are available to use, and you should recognize this as a linear equation. Okay. Now, wants us to find g of f, and now we have a number in here this time and an equation. Okay. So the first thing that we do is we put this -1 into the f function. So we want to find f of -1 first. So we have 2 over 3 minus 2 times -1, which gives us 2 over 3 plus 2, which gives us 2 over 5. So we have 2/5. When we plug our -1 into the f function, we end up with 2/5. Now we want to take that value and put it into the g function. So now we're doing g of 2/5. So we get 4 times 2/5 plus a. There's actually two ways that you can do it. This is the way I prefer. You could put it in algebraically first. In other words, you could put the 2 over 3 minus 2x into this x here, then plug in the -1 and work from there. But to me, putting the algebraic one in kind of complicates it. You can do it one at a time with numeric values. I think that's an easier way, but you could also do it the algebraic way. So I put in the -1 into f first, simplify it, then put that into the g of f, just work from your inside out, and then this value equals 8/5 plus a equals, where are we at? 3. Okay, so this equals 3, because this is our equation right here. Now we have to get rid of our fraction, so we're going to multiply both sides of our equation by 5. That's going to give us 8 plus 5a equals 15. So when we subtract 8 from both sides, that gives us 5a equals 7. And then we divide by 5. A equals 7/5, and that should be our answer there. Not really an easy way to double check that kind of a problem, but just follow the instructions again. G of f of x, x is now a number, plug it into the f function first, simplify that. So, just double checking really quickly, plus 2 gives us 2/5. Then we take that and plug it into the g function. Here's our x becomes 2/5. That's now 8/5. We have our plus a. Now we have our equation equals 3. Get rid of your fraction, multiply everything by 5, and then solve for a, and we get the value of a. So here's been several examples that involve composite functions, either simplifying an expression, solving for an equation, solving for the x, or solving for some other variable that's been introduced. And this should be part review and maybe a little bit expanded in the terms of complexity, what you had from the IGCSE material. So look forward to seeing you in our part 2, where we look at inverse functions. Thank you for joining me, and until next time, hope that you're able to do these complex parts of the Cambridge question types.